Hi there. Today we're going to go over the infinite series worksheet. Introduction to infinite series. What is a series? A series is an infinite sum. So remember what a sequence is. A sequence is a collection of terms. It's a function from the natural numbers to the real numbers and the list of outputs, A1, comma, A2, comma, A3. That is a sequence. But if we take those terms of a sequence and actually decide to add them together, we form a series, and it's known as an infinite series. So it's an infinite addition of the terms of a sequence. So we can write them just like A1 plus A2 plus A3 plus dot, dot, dot is a way of writing the series in a formal way, or we can use the formal summation notation of with the sigma notation, the sum of n equal to 1 to infinity of a sub n. So believe it or not, you'll have to suspend some of your belief, but some infinite sums out there actually converge to a finite number. So in order to determine or define the formal definition of a convergent series, we need to develop that definition. So let's first consider the sequence of partial sums. So what is a partial sum? It is a portion of the entire sum of the series. So S sub 1 here would just be the sum of the very first term. S sub 2 as a partial sum would be the sum of the first two terms. And S sub 3 would be the sum of the first three terms. And we know that the real numbers are closed under addition, so the sum of these is going to actually be a real number as well. So in general, the arbitrary partial sum of the first n terms would be a sub 1 up to a sub n. So if we actually consider a sequence of the S sub n, that would be here S1, S2, S3, S4, and that is a sequence, right? And if so we define the convergence of an infinite series, we know that our series is convergent if the limit as n goes to infinity of the partial sum actually converges and exists, right? So what does it mean to exist? S here would be a finite number. Make sense? So now you understand that in order to understand the definition of a convergent series, you need to know the definition of a sequence, and that is why we studied sequences and the limit of a sequence in section 11.1. Good. So if the limit as n goes to infinity of the partial sums does not exist or is infinite or negative infinite, then we say that our series diverges. And it does make sense that the limit as n goes to infinity of the S sub n, that would be S of infinity, right? And S of infinity, if that is actually a finite number, then we know that our series is going to converge. So the first type of series test that we're going to cover is the geometric series. And first, let's define what a geometric series looks like. A geometric series has a little bit of a structure to the terms of that sequence, or of the terms of the series. So if we look at this first rendition here, the sum as n equal 1 to infinity of a times r to the n minus 1. If we just write out the first couple terms of the series, we have this would be n equal to 1 here. And this would be n equal to 2. This term would be n equal to 3. So we can tell from just this expression as an example, this would be a times r to the 2 minus 1. And so we would have that that's a times r, or to the 3 minus 1, sorry. And that would be ar squared. So we do see that the structure of that sum from n equal 1 to infinity of a times r to the n minus 1 has this type of pattern where A and R are any real numbers. Good. So I'd also like to take the opportunity that the equivalent sum right here, you can also write your geometric series if we were to change the starting point of n equal 1 to n equal to 0, then we would actually change the n minus 1 to just n. Because if we started with n equal to 0, we would have a times r to the 0, and we'd have plus a times r to the first power. If we had n equal to 2, we'd have ar squared, n equal to 3, ar cubed, plus dot, dot, dot. And you can see that these two series here are equivalent. So that is something to take note of, that they would be, because this term actually ends up being just a, right? So it is equivalent to, it would be the equivalent sum of terms. Okay. So this is our very first series test, and it comes from one of the definitions or one of the theorems from the previous section, that if the absolute value of r is less than 1, then the limit as n goes to infinity of r to the n is going to equal 0. So we'll see this in a second with our proof. And for those of you studying mathematics, you might want to read this proof. This is a way of being able to determine what that expression for Sn could be if you wanted to use the formal definition of showing that the sequence of partial sums converges. So, and it's a pretty simple type of proof here, but the sum of the series, so notice here that if your absolute value of r is less than 1, then the sum of the series is convergent, and you can actually calculate the value of the sum, which makes it fun with some applications. So we would take a here, and we would plug in the a, and whatever r is, we would plug in the r down here, and we would be able to calculate, but we can only use that formula if the absolute value of r is less than 1. So if you read through the proof, they're trying to show that the sequence of partial sums actually goes to a finite limit. So, and if r is bigger than 1, then it would go to infinity. So here we see that we're using this case here as long as absolute value of r is within 1. Right? So in forming the partial sum S sub n, we've got a plus ar squared plus ar to the n minus 1, because we are working from the n equal 1 to infinity of ar to the n minus 1. Good. So if we were to multiply on both sides of the equation by r, right? Or we took this one and multiplied it by r on both sides, we would get, and distributing that r, each term would increase by a factor of r. Next, they do a simple trick where they take these two items, these two terms, and we'll do s sub n minus r sub n. We would just take those and that is, if you looked at it, a plus ar squared plus dot, dot, dot plus ar to the n minus 1. Take away ar plus ar squared plus dot, dot, dot plus ar to the n. We see that every single term, ar cancels with the ar squared cancels with the ar squared, because they collapse because you subtract them, and the only ones that are left are a and minus ar to the n. So then from here to here, we just factor out s sub n, and that's how we come up with an expression for s sub n. And so when we divide both sides by the coefficient 1 minus r, we would get a times, and this here, if we factored out the a, we'd get 1 minus r to the n. So that's how you get this expression here. And as long as And here we just put the a on the outside. So remember that theorem from section 11.1, the limit as n goes to infinity of r to the n equals 0 if the absolute value of r is within 1, because this is equivalent to minus 1 less than r less than 1. And so if we took the limit as n goes to infinity of s sub n, this r sub n, since n is the variable in this limit, r sub n is going to go to 0. And so we would just have a over 1 minus r, because 1 would be going to 1, 1 would be going to 1, and r here is a constant since n is the variable, and that would be going to r. And if r is bigger than 1, then r sub n would be going to infinity. Make sense? Good. So that's a pretty powerful one. It is one of the only types of series where if it is convergent, it's easy to find its sum. So again, often it is kind of difficult to find the expression for S sub n. And remember what S sub n is. It is the sequence of partial sums. But first, let's just continue with how do we work with the geometric series test. Here are some examples. Determine if the geometric series converges or diverges, and if it is convergent, determine the sum of that series. So I first want to note that we're starting with n equal to 1, and remember, we want to make it look like n equal 1 to infinity of a times r to the n minus 1 for the purposes of being able to identify a and for the purpose of being able to identify r. So we can put it into the formula a over 1 minus r. Or we want to make it look like n equal to 0 to infinity of ar to the n. So notice the difference. So here we want to make this look like n to the n minus 1. So I can actually see that I don't have very much work to do, because I can say that 1/2 to the n minus 1 is the same as 1 times 1/2 to the n minus 1. So I can tell here that a here is equal to 1 and r here is equal to 1/2. So my first test is the geometric series test. And I'm going to say, does the absolute value of r, is that less than 1? So I say, is the absolute value of 1/2 less than 1? Yes, it is. So I say, conclusion, my sum of a sub n converges by the geometric series test. Good. So it says if convergent, determine the sum of the series. So I can say that the sum is equal to a over 1 minus r, and my value of a was equal to 1, and my value of r was equal to 1/2. So I can say that this is 1 over 1 minus 1/2, and 1 minus 1/2 is 1/2, and 1 divided by 1/2 is equal to 2. Good. Now we get a little bit trickier here. So it's just a matter of playing with your exponent rules. And again, I want to note that we are starting with j equal to 0. So we want to make this one look like a times r to the j, right? We don't want it to be j minus 1. We want it to be j. So I have some j minus 1s here, and I have some j, but I'm going to first play with this expression. So I'm going to see that e to the j minus 1 over minus 4 to the j plus 1. Oops. So in order to actually get to j from j minus 1, I'm actually going to multiply on top and bottom by e. So I'm going to say that this is equal to e times j, or e to the j minus 1 over e to the minus 4 to the j plus 1. And now I can combine these two, and I can say that that's equal to e to the j over e to the minus 4 to the j plus 1. And now I actually want to take out one of the negative 4's because I want to reduce that j plus 1. So I'm going to say that this is equal to e to the j over e times minus 4. And maybe I'll make that into a different color because that's my 1. And then I still have that this is equal to minus 4 to the j, right? So that's equivalent. And now I want to take my exponent rules and combine these guys, right? So I'm going to say that this is equal to, and I can pull the minus 1 over 4e times, and I can say that this is e over negative 4 to the j. Make sense? Because I am using the rule a over b to the n is equal to a to the n over b to the n. So that's what I'm using here. I'm just working backwards, so I can put my e to the negative 4. So now I have this form that says this is my a times r to the n, or a times r to the j. So I can tell here that a here is equal to minus 1 over 4e, and r here is equal to e minus e over 4. Good? And remember here that e is roughly equal to 2.78 dot, dot, dot. Good? So now for my geometric series test, I can say is r, absolute value of r less than 1? Is negative e over 4 absolute value less than 1? Yes, because this is 2.78 divided by 4 is less than 1, right? So we do say that this series, a sub n, is convergent. So what is its sum? Its sum is going to equal a over 1 minus r, and my a here is negative 1 over 4e, and my r is negative e over 4, which is equal to minus 1 over 4e over 1 plus e over 4. And I tend to like to multiply on top and bottom by the lowest common denominator. So if I multiply on top and bottom by 4e, then I would get minus 1 over, and in distributing that, I get 4e, and then my 4 cancels, and I would get plus e squared, right? That make sense? Hopefully, right? Because then I would just distribute, these guys would cancel, and this 4 would cancel with this 4, and I would get e, and but I'd still have to distribute the 4e. Good. So one last one before we do other applications of the geometric series. Here we have m equal to 1. So we want to make this look like a times r to the n minus 1, or m, since we're doing m. Doesn't matter what your index is in that sum, just know that that is the variable. We want to make that look like that. So how do we do that? With the m plus 2, I'm going to start with this, and I'm going to say 7 times minus 1.01 to the m plus 2. If you wanted to play with these, this is just another example, but I can tell you now that because of that base of that exponent, we're probably going to get divergent because absolute value of minus 1.01 is not less than 1. But in playing with it, we could say that this is equal to 7 times minus 1.01 to the third power times minus 1.01 to the m minus 1, right? Because if we were to add these together, 3 plus m minus 1 is going to be m plus 2, right? And we are using a to the n times a to the m does equal a to the n plus m. So I can tell that this here is equal, this is going to be equal to my a, and this is going to be equal to my r. So a here is 7 times minus 1.01 cubed, and r here is minus 1.01. So my geometric series test tells me, does r, absolute value of r, is that less than 1? Is the absolute value of 1.01, which is equal to 1.01, is that less than 1? No. So conclusion, my series A sub n diverges by the geometric series test. And that concludes it for now. We'll return to the same lecture in a moment.